Welcome to this explainer. I'm absolutely pumped to guide you through this today. When we hear the phrase quantum computing, our brains usually jump straight to futuristic code and incredibly complex algorithms. But honestly, the biggest bottleneck in quantum right now isn't a software issue at all. It's actually a massive high-stakes engineering and manufacturing race. We're literally trying to build physical objects that behave as stable quantum systems. And as you're going to see, the methods being used to actually generate these qubits are completely mind-blowing.
Okay, let's dive into this. Here's the agenda for today's race. First, the quantum hardware challenge. Then, superconducting and trapped ion. Third, neutral atom and photonic. 4, quantum dots and topological. 5, diamond envy center qubits. And finally, the overall qubit tech race. So, Section 1, the quantum hardware challenge, the profound need for stability. To really understand this race, we gotta understand the hurdle we're jumping over. Now, a classical computer uses simple bits, right? Just a 0 or a 1. But a quantum computer uses QBITs, which can exist in a superposition of 0 and 1s simultaneously. But here's the thing. That magic comes with a massive catch, and that is physical stability. 15 millikelvin. To keep these incredibly delicate quantum objects stable, to stop them from losing their quantum state, some of the systems we're about to look at literally have to be kept near absolute zero. We are talking about environments colder than deep space. That right there is the true hardware hurdle we are desperately trying to overcome.
All right, moving to Section 2, superconducting and trapped ion, the heavyweight contenders.
First up, superconducting qubits. This is the most commercially mature tech out there right now, used by the big players like IBM and Google. And what's cool is they use semiconductor fabrication techniques that are actually pretty similar to how your regular computer chips are made. So, when metals like aluminum or niobium are cooled near absolute zero, their electrical resistance just totally vanishes. Millions of electrons pair up into what are called Cooper pairs, and they start acting together as one single quantum object. It's wild. The manufacturing process here is super fascinating. It starts by cleaning a pure silicon or sapphire wafer. Next, a hyper-precise, incredibly thin layer, like 50 to 200 nanometers thin, of superconducting metal is deposited using methods like sputtering. Then, UV light transfers the circuit patterns right onto the wafer. But the absolute heart of the qubit is step 4, creating the Josephson junction. This is a tiny 1 to 2 nanometer insulating barrier, essentially sandwiched between two superconductors, kind of like an aluminum oxide layer between aluminum. Finally, this whole chip gets packaged up into a dilution refrigerator to hit those extreme temperatures. And honestly, this hardware ends up looking like some giant golden sci-fi chandelier.
So, the crucial point is weighing these stats objectively. On the plus side, we have very mature fabrication techniques that we already understand from the broader semiconductor industry. We've got incredibly fast gate speeds and a massively strong ecosystem backing it up. But the challenges are real. That extreme cooling requirement is a huge logistical headache, and these qubits are insanely sensitive to noise. So rigorous error correction isn't just nice to have, it is absolutely required. Next up, we have trapped ion qubits, championed by companies like IonQ. Now, instead of printing a circuit, this technology goes a completely different route. It uses individual charged atoms, like ytterbium or calcium, just suspended in a vacuum. To generate these, the process starts by creating an almost perfect vacuum, pushing pressures way down below 10 to the negative 11th torr. Then atoms are introduced, and a laser comes in and strips away exactly one electron. This ionizes the atom, giving it a positive charge. And because it's charged, it can be captured in an electromagnetic Paul trap. This means it literally floats in free space, zero physical contact whatsoever. From there, lasers cool the ion all the way down to the microkelvin range just to slow its motion. Finally, these incredibly complex laser pulses manipulate the internal energy levels of the atom to actually perform the quantum operations.
Let's look at their stats, kind of like a sports commentator evaluating a player. The massive advantage here, extreme accuracy and incredibly long coherence times. Because they're perfectly isolated in that vacuum, they just don't easily lose their quantum state. But what's the trade-off? Well, you're dealing with sluggish operation speeds compared to those snappy superconducting chips, and you're relying on highly complex laser systems that are, quite frankly, really difficult to scale down.
Let's move along and see how this builds in Section 3, neutral atom and photonic, giant atoms and light.
Neutral atom qubits use uncharged atoms, like rubidium or cesium. The generation begins with laser cooling them down near absolute zero. But then, the real magic happens in step 2.
Highly focused lasers literally act as optical tweezers to trap and perfectly arrange these individual atoms into highly programmable, flexible grid patterns. Now, to make them interact, laser pulses excite these atoms into what physicists call Rydberg states. They temporarily inflate into these giant, high-energy atoms that strongly interact with their neighbors. This allows for quantum entanglement purely through proximity. It's like they're just reaching out and talking to each other.
The advantages here are honestly stunning. Because you're using those optical tweezers, you can pack thousands of qubits together in highly flexible dynamic layouts. However, because it's a relatively emerging technology, the main challenge is that the robust error correction you'd need to make this perfectly reliable at scale, well, it's still actively being developed.
All right, shifting gears entirely, we have photonic qubits, used by companies like PsiQuantum. Instead of trapping atoms or electrons, this tech uses single particles of light, photons, to carry quantum information in properties like their polarization or their path. Generating these is tricky. It requires single photon sources like quantum dots or a specialized process called parametric down conversion. But once they're generated, these photons travel down these tiny optical highways called waveguides. We're talking hundreds of nanometers wide, etched directly into silicon or silicon nitride. The photons get routed around using microscopic beam splitters, and finally they're measured using highly sensitive single photon detectors.
And this brilliantly illustrates a massive operational advantage. Photons do not need to be frozen. This tech actually allows for room temperature operation, and it offers absolutely stellar networking capability right out of the gate simply because the information is already in the form of light. The main hurdles keeping them from crossing the finish line? Well, actually, generating high-quality single photons on demand is technically super difficult, and so is perfectly efficient detection without losing any of that precious light along the way.
Okay, moving right along to Section 4, Quantum Dots and Topological, Electrons and Exotic States.
So, quantum dot qubits. These are being pursued by folks like Intel and Dirac, and they use individual electrons trapped in semiconductor structures made of silicon or germanium. The absolute genius of this approach is step 1, using standard CMOS fabrication. This is the exact same manufacturing process used to make the chips sitting in your laptop right now. They form tiny metal gates that create highly specific electric fields to trap and confine just one single electron in a nanoscale region. Once that electron is confined, microwaves are used to precisely rotate the electron's spin. Spin up is a 1, spin down is a 0. Simple as that.
The major appeal here is unmatched scalability. Because these are fully compatible with existing multi-billion-dollar chip fabs, the potential is that we could eventually just stamp out billions of qubits. But making these requires mind-bending atomic-scale precision. Literally, a single misplaced atom in the silicon lattice can completely mess up the electric field and cause you to lose the electron. So, high risk, high reward.
Now for arguably the most exotic competitor in the race, topological qubits, pursued primarily by Microsoft. Now, these don't just use a single particle. Instead, they rely on Majorana zero modes, meaning the quantum information is actually stored across physical space rather than at one specific point. To generate these, you start by growing extremely thin indium arsenide nanowires. Next, these wires are coated with an aluminum superconductor. Finally, when a very precise magnetic field is applied, these exotic topological states are created and the Majorana modes appear at the absolute opposite ends of the wire.
The theoretical upside here is just enormous. Because the information is physically spread out, it actually has built-in protection against local noise. That leads to potentially ultra-low error rates. But we have to clearly note the stark reality on the challenge side. Foundational experimental verification of these states is incredibly complex, and honestly, it's still very much an ongoing process in laboratories today.
Section 5. Diamond NV Centers. Microscopic Flaws.
This one is so cool because you literally build these qubits by creating a defect. The process begins by actually growing synthetic diamond using chemical vapor deposition. Then, you purposefully implant nitrogen atoms right into the diamond lattice. Through ion bombardment, you selectively knock out an adjacent carbon atom, which creates a vacancy right next to the nitrogen. After a heat treatment called annealing to stabilize the whole thing, boom, you have a nitrogen vacancy or NV center. This tiny defect traps an electron, and that electron's spin becomes your qubit, which you can then initialize and read using very precise lasers.
Now, what's really interesting about this slide is the unique combination of advantages. The incredibly tight crystal lattice of the diamond protects the electrons so well that these systems offer wonderfully long coherence times. And they operate near room temperature. No giant dilution refrigerators required. However, isolating a single defect is one thing. Figuring out how to wire millions of them together into a large-scale integrated computer, that is an enormous, currently unresolved engineering hurdle.
And that brings us to the final stretch, Section 6, the qubit race, evaluating the landscape.
Taking a look at this summary, it highlights exactly why this is such a fierce, multifaceted race. You've got superconducting, quantum dot, and topological qubits fighting tooth and nail to perfect microchip-style fabrication at absolute zero. On the other hand, trapped ion and neutral atom systems are busy mastering the delicate manipulation of individual atoms floating in perfect vacuums. Meanwhile, photonic and diamond and V technologies are desperately trying to bypass those extreme cooling requirements altogether. The entire industry is searching for the perfect balance of scalability, high fidelity, realistic manufacturability, cost-effectiveness, and robust error correction. And as of right now, honestly, no definitive winner has emerged.
Which leaves us with the ultimate question. Which physical implementation will ultimately win the race to scalability? Is it going to be the giant superconducting circuits, the ultra-precise floating ions, or maybe something as exotic as a topological state? I really invite you to keep these distinct manufacturing methods in the back of your mind as you watch the news in the coming years. Because understanding the hardware under the hood, that is the absolute key to understanding the future of quantum computing. Keep learning, keep questioning, and I will see you in the next explainer.